our last lesson, we took a look at the ionic bond and how metals will lose electrons and nonmetals will gain electrons to achieve that noble gas configuration, the octet rule. In this particular lesson, we'll examine what are known as covalent bonds, where nonmetals come together to share electrons and again to achieve their noble gas arrangement. So the sharing of electrons, very different than the ionic bond that transferred electrons. If we take a look at an examination of a covalent bond, we see many interactions, basic law of electricities where opposites attract, likes repel. Let's suppose here we're looking at a hydrogen nucleus with a single proton. This would represent the second hydrogen in a molecular form, so just kind of thinking H2 perhaps. It's just a nice example. We would see that there's intermolecular attractions, the attraction between electrons and the nuclei. You can clearly see that's an attractive force where negative and positive are definitely attracted to one another. However, we see that there's a repulsive force, and in that repulsive force we would see that the two positives repel and the two negatives repel. How might the electrons arrange themselves to alleviate the repulsions and gain more attraction? And you can examine the way that they've done that with this electron distribution. Notice where the greatest amount of electron cloud distributes themselves is between the two nuclei. And this heavy region here is in fact what we call a covalent bond, the sharing of electrons. So the electron from this hydrogen is zipping around, traveling around either one of the nuclei, creating this cloud-like appearance, kind of like a figure 8. And this heavy region of electron density is known as a covalent bond. Each one of those nuclei sharing the pair of electrons. We have attractions between the electrons and the protons in the nucleus. We have electrons repelling, and we have the protons in the nuclei repelling. So by creating this distribution of electron cloud between the two nuclei, we have indeed alleviated most of the repulsive forces between like charges. The attractions between nuclei and the electrons cause the electron density to concentrate between the protons of the nuclei. And as a result, what we have stated, the overall electrostatic interactions are attractive by nature. By placing the electron density between the two protons, between the nuclei, we alleviate repulsive forces and we gain more attractive forces. And this shared pair of electrons is known as the glue that binds the atoms together. The definition of a covalent bond, the sharing of electrons between two nuclei. Let's examine some simple models using some Lewis structures. We can begin with the simplest structure of all, a hydrogen. Notice that hydrogen, who lives in group 1a, has one valence electron. If we were to write its electron configuration, nothing simpler. One valence electron in the first energy level in the s sublevel. We would represent that with a single dot. The second hydrogen in the molecular form, also with its 1s electron, placing it in its valence shell of s, and the shared pair is drawn with a solid line between those dots, a shared pair of electrons, a single covalent bond. One shared pair is known as a single covalent bond. Thinking about the orbital diagram, we could represent this as the S. This guy would have to be spinning down, and if they combine those shared pairs, think of that now as one orbital, one spinning up, one spinning down. We've now shared a pair of electrons. What about molecular chlorine, Cl2? Well, chlorine, who lives in the 7th family, group 7a, would start with 7 valence electrons, one around each side first, seeing that the 7th has a lonely spot, an open spot for bonding. If we were to draw in the second electron dot structure for the atom of chlorine, we would see that its 7th electron here could then form what's known as a single covalent bond. Attach the two dots and you come up with the molecular formula for chlorine, Cl2, yet another single covalent bond. The shared pair of electrons now creating a larger orbital between the two nuclei sharing the pair. By the way, those are two dots. They kind of ran together when I drew. There we go. What about an ammonia molecule, NH3? Think symmetry. When I start thinking about drawing these, I'm going to select the atom nitrogen to be in the center. It's the atom I have just one of. A nitrogen who lives in group 5A with its 5 valence electrons. 1, 2, 3, 4. Doesn't matter. I'll just place it on top. There's my 5th electron, group 5A, 5 valence electrons. Now I can see the hydrogens with their open spots for bonding. Each of those then placing its electron to a shared pair and just really filling the holes, creating an ammonia molecule. Now each hydrogen has 2 electrons. Its noble gas configuration of helium has been achieved. And the nitrogen now has 8. Its noble gas of neon has now been achieved. So if I were to count these, 1, 2, 3, 4, 5, 6, 7, 8 pairs, or 8 electrons, 4 pairs. We see that there are one unbonded pair and 3 bonded pair in an ammonia molecule. And there's one more in this, methane, CH4. Let's draw that. The molecule of methane, again, pick the carbon as the central atom. Carbon has 4 valence electrons living in group 4A. We can see 4 open spots for bonding, and I'll simply attach each of those hydrogens, showing very simple models just to get our feet wet with a covalent bond. 4 single covalent bonds as we drew the hydrogens around each. So here we would have 4 single covalent bonds, all 4 of them bonded. Very simple models for single bonds. Sometimes in order to achieve the noble gas arrangement, we'll end up drawing what are known as multiple bonds, either double or triple, but there really is nothing bigger than a triple covalent bond. If we consider a molecule of carbon dioxide, carbon with its 4 valence electrons will have 4 dots coming from the carbon. Oxygen, who lives in group 6A, has 6 valence electrons, which will give us a total of 12. 12 plus 4, we get 16 dots by the time we're done. Alrighty. So considering carbon is the central atom, so atom I have just one of, and think symmetry. I don't want to crowd the molecule, so I can either do top, bottom, or left and right. I'll go ahead and place an oxygen on either side. Now I've placed 4, leaving us 12 more. That's all the dots we get, 12 more coming from the oxygen. So here we'll place 1, 2, 3, 4. There's a bond. 5, 6. Come over on this side, do the same. 1, 2, 3, 4. There's a bond. 5, 6. That will work. But clearly you see that not everyone is partnered. Not everybody has the 8 that it so demands to be an octet. We have a lonely electron here and a lonely electron here. Why don't we bring them up to the center and share between the symbols? We'll share another set of electrons. We can do the same with these electrons. Bring them into the center and share a pair of electrons. So drawing this again just cleanly, we'd have O double bond C, double bond O, with 2 pairs of electrons on the oxygen that are unbonded. Boy, that's not coming out very clean. I apologize. 1, 2, 3, 4. No line between them. They're just dots. Alrighty. C double bond in either direction to the oxygens. Now I can clearly see that oxygen has 8, 2, 4, 6, 8. Carbon has 8. They're all bonded, as well as the other oxygen. So here we drew what are called double covalent bonds, drawing 2 shared pair. And the nitrogen, N2. Nitrogen has 5 valence electrons, so we get a total of 10 dots by the time we're done. So nitrogen, 1, 2, 3, 4, 5. Let's connect it to the second nitrogen. 1, 2, 3, 4, 5. I see a bond there. Lonely electron, bring them together. Lonely electron, bring them together. Cleaning it up, we have a triple bond, N triple bond N, with a set of dots on either side. And as a rule, the distance between the bonded atoms decreases as the number of electron pairs increases. I can't stress enough that this is really something critical to understand. You will see this come up over and over and over again about bond lengths. Let's take a moment and just kind of digest what this is saying. As a rule, the distance between bonded atoms decreases as the number of shared electron pairs increases. Suppose I have a molecule, CH3, CH3, with a single bond and these are hard to draw. Those H's come out. Here we go. CH3, CH3, with a single bond, a very long bond. And this is one single bond, very long. What if we were to draw a double bond, and now we would only have 2 hydrogens left on it because we moved a shared pair. So this molecule, CH3, CH3, this molecule now, CH2, CH2, shorter distance because of the double bond pulling these atoms closer together. And if we were to draw a triple bond, and we'd only have 1 hydrogen left, we'd have HC, CH, just trying to drawing it that way. This would be the shortest bond of all. And maybe I should stress that with better drawings. Very close distance. So the shortest bond. So singles are the longest bonds. These are a little bit shorter. And these are shortest. Alrighty, so the longer the bond is the single bond. They draw the atoms closer together if you're sharing more electrons, and the atoms are extremely close together in a triple bond. So bond length is what's being discussed in this last bullet. Now, we've been looking at shared pairs of electrons, but just because we're sharing something doesn't mean that they're being shared equally between the 2 nuclei. And that's the topic here brought up as a polar covalent bond. The term polar means that we have regions in the molecule that have different sets of charges distributed within it. Now, let me just kind of clarify in terms of a, how about a bar magnet? If you've ever looked at a bar magnet, you'll see an end that's stamped positive and an end that's stamped negative. In a magnet, it contains 2 different poles on it, a negative pole and a positive pole. It is known as a dipole. Any structure that has a region with negative charge and a region of positive charge, 2 different charged areas, is known as a dipole. To be polar means that you have regions that are more positive and regions that are more negative within the same structure. Although atoms often form compounds by sharing electrons, those electrons are not always shared equally. If I have an electron being pulled towards more electronegative element, we'll see a region set up that's more negative and a region set up more positive. Here's an example of molecular fluorine. So just simply a fluorine attached to itself. And we would see that there would be 3 sets of non-bonded pairs of fluorine in its Lewis dot structure and 1 single bond between them. The atom of fluorine bonded to itself, well, no atom is stronger or has more of a pull on the electron if they are indeed the same atom. They're built equally. So we have an equal distribution of charge. This molecule is nonpolar. There's nothing of interest in terms of the color on this slide, is there? Look at the HF molecule. H bonded to an F. Now hydrogen, of course, would have no unbonded pairs of electrons on it. It's simply attached to a fluorine who has 3 unbonded pairs of electrons. The pull of the electron density is clearly being pulled towards the fluorine nuclei, leaving this particular region more positive and this particular region more negative. Now I want us to examine what I've just drawn here, a polar covalent bond, where the area that is positive has a little tail on it with what looks to me like a positive sign. When I see this, this is showing me the more positive end of the molecule. The tail is positive, but the arrowhead points to the more negative region. Point at the more negative region, leaving hydrogen left as a little bit more positive and the fluorine left with a little more negative distribution of the electron cloud. Clearly fluorine, the stronger, more electronegative element, is pulling the shared pair of electrons towards itself, leaving the hydrogen electron distribution lower as compared to the fluorine's electron distribution. The color is showing me a polar covalent bond. This area of the molecule is partially negative. This area of the molecule is partially positive. Sorry for that pop-up. The little Greek symbol, a squiggly little s, denotes partial. Partially negative, partially positive in this polar molecule. I would certainly consider writing into your notes, because I know the picture isn't there, but this does an excellent job of showing the color distribution of a polar covalent bond. Fluorine end of the molecule has more electron density than the hydrogen end. Clearly we see the distribution of electron cloud pulling towards fluorine. I introduced something very important, a polar covalent bond pointing at the more electronegative element, the stronger, more polar bond. This guy right here, nonpolar, an equal sharing of the electrons. No element is stronger than the other pulling the electrons because they're the same atom. So nonpolar, a covalent bond in which one of the electrons is shared equally between the two atoms, just as in the fluorine we drew, or perhaps if I were to draw the molecular compound chlorine, same atom, nobody stronger than the other, or we drew a little bit earlier the nitrogen with its triple bond, nobody stronger. Those are all nonpolar molecules. It's hard to draw dots, I'm finding out. I apologize. Those are dots, and then the computer program fills them in as a line. These has 2 dots, but these are nonpolar molecules, equal distribution of those bonds. However, a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other. If the difference between the strength of those two atoms is so strong, one of the atoms might just rip the electron away and actually force an ionic bond, a complete transfer. So let's not confuse, like, these are shared pairs. If they were so strong in comparison metal to nonmetal, for instance, a nonmetal can just rip the electron right off of a metal's electron distribution, and now we have a transfer. Polar bonds are shared pairs, it's just that they're not being shared equally. Somebody has a greater control over it. And how do we go about determining who's stronger than whom in this periodic table? And this is the term called electronegativity, a very important term in chemistry. Electronegativity. The strongest of strong, most attractive atom pulling electrons towards itself is fluorine. The smallest of our atoms, isn't it? If you think about who's the smallest atom on our chart, fluorine, the strongest, most active non-metal. Fluorine, with its electronegativity value of 4.0, is indeed the highest value on our chart for electronegativity. Look down here. Who's the least likely to want to gain an electron? That's cesium, isn't it? Opposite ends of the chart. Oh, now I'm going all over. So here we have an opportunity. Let me clean up my screen. I'm going to think about opposite ends. See where the cesium is? Let me just move that out of the way. Here's the cesium. Here's the fluorine. Opposite ends. Fluorine, the most electronegative. Cesium, the least electronegative. So what we're noticing is a trend. The ability of atoms in a molecule to attract electrons to itself. The trend shows electronegativity increasing as you point towards fluorine and actually decreasing as you go down a column. So bottom right, most metallic, least electronegative. Top right, these are the nonmetals. Fluorine is the strongest of nonmetals, so it's important to note this electronegativity trend. Perhaps you'd like to add that to your test-taking tool. The trend itself says electronegativity increases from left to right and from the bottom to the top. So you could say it's increasing as you go up, it's increasing as you go left to right. These values assigned to each and every atom compare the strength of the atom to that of fluorine. Fluorine given the top value of 4.0. Now what we'll look at is what's called an electronegativity difference to determine what type of bond is actually formed. Is it polar, is it nonpolar, or is it indeed ionic? Let's review some important vocabulary. And coming back from Chapter 7, we had some periodic trends. And in Chapter 8, we're introducing a brand new word called electronegativity. This is the ability of an atom in a bond, in a molecule, to attract electrons to itself. So if I were to consider HF, fluorine is more electronegative than hydrogen. Fluorine distributes the electron density towards itself, pulling the electron shared pair away from hydrogen, but it's clearly saying in the molecule. Now in last chapter we defined ionization energy and electron affinity, and I just wanted to review those terms. How strongly an atom holds on to its electrons as ionization energy, and the measure of how strongly an atom attracts additional electrons is an affinity. This is a single atom, not in a molecule, but a single atom. Ionization energy, let's say a potassium in its gaseous form loses an electron, becoming a positive ion in its gaseous form, losing an electron. This we've practiced as ionization energy, the energy associated with a gaseous atom losing an electron. Associated with electron affinity would be a gaseous atom gaining an electron. Let's say, for instance, chlorine in its gaseous form gaining an electron, forming its ion in a gaseous form. Chlorine atom gaining an electron, becoming -1. This is called electron affinity. The ionization energy is losing the electron. Notice these are single atoms in a measurement of their energy, kilojoules. Electronegativity is different. It's talking clearly about electrons in a shared pair. And in a shared pair, what we're looking at is who is the stronger, more electronegative element, being able to distribute the electron cloud closer to itself. And that chart that we're looking at really is helpful. And I printed a separate one that we'll look at. What I'm going to do is show this chart. And when I do that, let's see if I can get it to pop up. I can't get it to pop up, but I will give you an electron distribution chart as a test-taking tool page. HF, hydrofluoric acid, or hydrogen fluoride if it's in a gaseous phase, a very polar bond. Very polar. Electronegativity difference between H and F is 1.9. Let's kind of see what that means. Hydrogen value 2.1. Fluorine value 4.0. The difference between H and F, subtracting those, gives me a 1.9 polar covalent bond. So I'm seeing that's where this value came from, just subtracting the H and the F, and I get a difference. The greater the difference, the more polar the bond. A very, very, very strong electron distribution towards the H to the F. HCl, bond length is a little larger. So the H and the Cl are not as close together. HBr an even longer bond, HI an even longer bond, because as we move down the column, the electronegativity is decreasing. If fluorine is the strongest of strong, chlorine a little bit less, bromine a little bit less, iodine a little bit less. You can see the trend decreasing as you go down the column. And when that happens, you see that the polarity of the bond is actually decreasing as well. Chlorine, not as strong as fluorine, so the electron distribution still very polar, but just not as colorful as HF. Notice that it's a larger molecule. Notice that the reds are now disappearing, blues are disappearing, the electron distribution is becoming greater, and here HI, with the longest bond of all, the least electronegativity in terms of difference, and this is getting annoying, my apologies. So the dipole moment is smaller. It means that the electron distribution around those two atoms is actually more even than they are with a more polar bond. Polarity. Polarity simply means in a shared pair of electrons who has greater control. If I subtract the two atoms in a bond and they come out to be exactly 0, it's a nonpolar bond. If I subtract the two atoms in a bond and it lies in a range of 4 to 2.1, we have a polar covalent bond. And here, if it comes greater than 2, we have an actual ionic bond, as in lithium and fluoride. Alrighty. So take a note here. Very important side note. 3 to 4, you're looking at very electronegative elements. By the time you get less than 1.5, which is this area, these are not electronegative elements at all. So you're looking at the electron distribution pulling towards the top right of the chart. Let's take an example. Which bond is more polar? Indicate each case which atom has the more partial negative charge. Boron in chlorine or carbon to chlorine. I'm going to need a tool page. Boron has a value of 2.0. I'm going to just jot that so I remember 2.0. Chlorine has a value 3.0. Let's just jot that so we remember. The difference between boron to chlorine is a 1. Let's find carbon. Carbon has a value of 2.5. Chlorine still a 3.0, so this value is 0.5. Which bond is more polar? Indicate the case in which the atom has the partial negative charge. Well, so clearly the greater the difference, the more polar the bond. BCl is more polar, and so therefore we'll show that polar bond by showing the distribution of chlorine pointing at the more negative chlorine, leaving boron partially positive. The difference in the electronegativities, chlorine and boron, we decided was 1.0. When we solved for the difference between chlorine and carbon, it was 0.5. Therefore, our boron-chlorine bond was more polar, a greater electronegativity difference. We decided the chlorine carried the more partial negative charge because it had the higher electronegativity value.